Critical Thinking Rule 7. Use more than one example. This is first in a series of videos about arguments by example. A generalization is a statement about the properties of a set of individuals. There's a widespread misconception that all generalizations are problematic, but generalizations can be true as well as being false. Examples of true generalizations include the information provided to us by mathematics and much of the knowledge that comes from sciences. For example, all triangles have angles summing to 180 degrees. All protons have a positive charge. All atoms have at least one proton. All water molecules have one oxygen atom and two hydrogen atoms. These are all true generalizations, and it's very useful to know them. So when Mark Twain says jokingly all generalizations are false, including this one, his claim is actually misleading because some generalizations are false, some are inadequately justified, but many are true and adequately justified. So don't confuse generalizations with overgeneralizations. Overgeneralizations are either false because they claim that all or most members of a particular set have a property when they don't, or they're just inadequately justified because they're generalizations with not enough examples to support them. This series of videos is about how to prove generalizations using examples. So let's talk about some different kinds of generalizations. Universal propositions of the form all x's are y's are only one kind of generalization. An example is all cats have tails. But there are other kinds of generalizations. Another type of generalization includes the various information that can be given to us by statistical analysis of a data set, such as average value, median value, standard deviations, and so on. The difference between the statistical value and a universal proposition is that universal propositions are meant to apply to each member of a set or group individually. If you say that all cats have tails, that means that each individual cat has a tail. Whereas if you give a statistical average, that's not making a claim about each individual value in a set of data. It's a claim about the values as a whole, but it still counts as a generalization because it applies to a group or set of things. We also have statements of proportion. For example, 72% of female U.S. 2014 high school graduates enrolled in college, whereas 64% of male U.S. 2014 high school graduates enrolled in college. You're not saying something is true or false about all female U.S. 2014 high school graduates and so on. You're making a statement of what proportion of this group has a certain value or property. There's also statements of probability, which can be thought of as types of statements of proportion. An example is there is a 40 in 52 chance that a card randomly drawn from a deck is a numbered card and not a face card. So this is basically saying what proportion of cards have this certain value or property. But the difference is that a statement of probability is phrased such as to apply to an individual card, in this case drawn from a deck. So you can talk about the probability of one member of a set or group of things having a certain property. So let's distinguish between universal propositions and particular propositions. Universal propositions are only one type of generalization, but they often show up in logical arguments. Universal propositions are of two main kinds. All A's are B's and no A's are B's. Both of them are claims about all members of a group or set. An example of the former, all cats have tails. Of the latter, no oxygen atoms are metals. Particular propositions are about one or an indefinite number of members of a group. They have the form some A's are B's or some A's are not B's. An example of the former, some Americans eat burgers. Of the latter, this cat does not have a tail. Particular propositions never count as generalizations because we don't know how many or what proportion of a group they apply to. They give us no sense of an average value, for example, or of the frequency or distribution of a property within a group, so they don't count as generalizations. So let's talk about proving generalizations. There's two main ways to prove a generalization. One involves reasoning from other generalizations. It's not what this chapter is about. It's mainly about the second type, but it's worth distinguishing between the two because both are common. So let's give an example of reasoning from other generalizations. All humans are mammals. All mammals are vertebrates. Therefore, all humans are vertebrates. This is a logically valid argument, but notice it does not involve giving particular examples to support the generalization. A second way to prove generalizations is by giving particular examples to support it. So for instance, Socrates is a human and a vertebrate. Mark Twain is a human and a vertebrate. Therefore, all humans are vertebrates. This is not a particularly strong argument because we only have two examples to support the generalization, but it still illustrates the concept. And it's this second type of reasoning that this chapter is mainly about. In order to understand and evaluate arguments for generalizations, it's helpful to use the statistical concepts of populations and samples. A population is a set, group, or class of things that a generalization is about. Don't be misled by the word population. This does not only refer to groups of people. You can generalize about any type of thing. So for example, you could talk about the population of galaxies in the universe. A sample is a subset of a population whose properties are examined in order to generalize about the population as a whole. So oftentimes it's not practical to make a generalization or to prove a generalization by looking at all members of a population. So for example, if we wanted to generalize about the behavior of hydrogen atoms, it's impossible physically to examine all of the hydrogen atoms in the universe. Instead, we look at a sample of hydrogen atoms that we have under controlled conditions that are easy to access, etc. And then we try to generalize about the entire population. So that's the basis of this type of reasoning. We're looking at a sample, which is the number of examples, and then trying to conclude something about the whole population. So an argument by example, or an inductive generalization, is an argument that a generalization about a population is true because it is true of a sample. So an example of that type of argument: these swans are white, therefore all swans are white. Interestingly, all arguments by example are logically invalid. An invalid argument is one such that even if the premises are all true, the conclusion could still be false. There'd be no logical contradiction with this type of argument to have true premises and a false conclusion. So let's think about why that is so. There are good arguments by example, and yet they're all invalid. Why is this? Well, if you think about the argument for swans, no matter how many white swans we've observed, thousands, hundreds of thousands, even millions, all it takes is one new observation, one black or other non-white swan, to disprove our generalization. The thing is, this does not just apply to the case of the swan argument. Any argument that generalizes about the world or about reality based on examples have the same logical structure. So for instance, we have generalizations about the behavior of different types of atoms, and about different types of molecules, and about different types of other physical objects such as stars. Especially when we get down to the basic constituents of matter and energy, like atoms and subatomic particles, we don't expect the generalizations we've observed to suddenly be violated by the universe. But logically speaking, it's totally possible. Just because all the electrons we've previously observed behave a certain way, there's no logical guarantee that future observations will fit this pattern. So there's no logical contradiction from saying that our beliefs about electrons, etc., could be false. And it's more easy to see this in the case of the swan example, because this has actually happened historically. If you live in parts of the world where all the species of swans are white, then you could observe many, many swans before you observe one that's black from a different part of the world, say. But logically speaking, the same problem affects all of our arguments by example. However, arguments by example can still be logically strong, even though they're invalid. Validity and strength are the two main ways of evaluating an argument, logically speaking. A valid argument is one where if the premises are true, then it's logically necessary that the conclusion is true. A strong argument is one where if the premises are true, the conclusion is probably true. So strong arguments don't give you the same level of proof, the same degree of certainty in the conclusion based on the premises. However, strong arguments are still very useful. In fact, much of our knowledge about reality is based on arguments that are strong but not valid. So there's nothing inherently wrong with a strong argument. Just keep in mind it's a different level or degree of proof. And the conclusions of strong arguments can always be proven false based on additional information, even if the premises of those arguments were true. Another type of inductive argument that's similar to inductive generalization or argument by example is argument from generalization. So an argument from generalization is an argument that claims that because all members of a population probably have a property, then a particular member or subset of the population also has that property. So the difference between this and argument by example is an argument by example, you're arguing from the sample to the population. In argument from generalization, you're arguing from the population to the sample. It's the logical converse. It's like a switcheroo. So here's an example of argument from generalization. All swans are probably white, therefore this swan is white. Or you could say, therefore the next swan we observe will be white. So the thing that this has in common with arguments by example is they both involve generalizations. Arguments by example have a generalization as the conclusion. Arguments from generalizations have a generalization as a premise. And the other thing about arguments from generalizations is that they involve a notion of probability of proof of the premise. So there can be other types of arguments where you have a premise that's a generalization and a conclusion that's a particular claim, but they don't count as arguments from generalization, at least not in the same sense. For example, all triangles have three sides, therefore this triangle has three sides. This is a valid argument because if we're making the claim, our premise, as applying universally with complete certainty, then we're certain that if that premise is true, the conclusion must also be true, so it's valid. Arguments from generalization are invalid, but they can be logically strong. So if there's sufficient probability in the premise, that carries over to the conclusion. Because it's probably true that all swans are white, therefore this swan is white, we can make that inference with some degree of probability. Rule 7 says use more than one example, but this is somewhat vague. How many examples do we need to support a generalization adequately? So take as an example the generalization, all Americans eat fast food. How many examples would we need to support that generalization? The answer is it depends. There really is no single answer to this question, but there are several factors that determine how many examples are needed to increase the probability that a generalization is true based on those examples. So we'll examine each of those factors in turn. First, the larger the sample size, the greater the probability that the sample matches the population, all things being equal. And that's what Rule 7 is getting at. The more examples, the merrier. So the sample size is the number of examples we have, the number of individuals that we're putting in our sample, that we're getting data or properties from. So all things being equal, larger sample sizes are better. There's no specific magic number that makes the argument valid. Inductive generalizations are always invalid. They're always a matter of probability. So the more examples, the better in most cases. The only exception would be if you're taking a biased sample, and so the more examples you get, the more it biases your results. We'll talk about this in a later video, but all things being equal, larger sample sizes are better. Now, another factor to consider is how large the population is that you're generalizing about. In general, the larger the population is, the larger the sample needs to be in order to support a generalization. So if you're only generalizing about a small number of things, such as students in one classroom, for example, or teachers in one particular program, you don't need as many examples as if you're generalizing about a large number of things, such as all Americans. Thirdly, the less certain you are about the sample being representative of the population as a whole, the more examples you need in order to support the generalization adequately, the larger your sample needs to be. This is the most subtle of the three criteria for how many examples you need, but it's often the most important. So basically, if you have some reasonable certainty that the sample you're looking at is not biased, that it's likely to be representative of the population as a whole, you don't need as many examples as you would if you were less certain about that. So take an example of electrons. There's no particular reason to suspect that the electrons we're observing on Earth are fundamentally different from those that exist in distant parts of the universe. And so even though those electrons are highly biased in terms of where in the universe they're from, there's no particular reason to believe this is going to bias our generalization about electrons as a whole. Conversely, imagine that you're trying to figure out what proportion of bears have brown fur, and you're only looking in one particular geographic region. Then that's going to be a biased sample. You're only looking at bears, for example, in Southern California or in Alaska. It's going to change the results of your analysis. So in general, the less certain you are about your samples being representative of the whole population, if you have good reason to believe that some aspects of how you collected data from the sample are going to bias the results, the more examples you need to help support the generalization. Next up is Rule 8, use representative examples.